Okay, so now we're going to talk about gravity wall systems. So this is the gravity wall part of this discussion. We're going to look at a bunch of different gravity walls, but I'm going to concentrate on one in particular. So the way we apply earth pressures for the gravity wall is going to be different than the way we did for the cantilevered wall, so you got to make sure you get that right. And then we're going to have the same external failure modes, but the design process is going to be slightly different, so you need to do that. And then we're going to have a completely different internal design. And I'll come back here after I go through the learning objectives and talk about external versus internal design, because I just went through that with the cantilevered wall, but I'm not sure I made that distinction clearly, so I'll do it in just a second. And then there's a bunch of gravity wall systems. We talked about them in the first lesson. And I've given you some design guidelines, which I'll go over here at the end of this presentation quickly, for some other systems. But we're going to design a gabion wall. And I picked a gabion wall in particular because the internal design guidelines for that are well published and easy understood, where some of these other ones are very proprietary, and they give you these little design calculations you're supposed to do, and you don't really know what they're doing. So it's a really good gravity wall system, I think, for you to get experience designing, and it's a pretty common one that can be very useful. So that's, and I've already posted a design problem for you guys to start work on and turn in next week. All right, well, so I think I've shown this picture before. I use this one a lot because I don't know where this is like the best set of stone masonry gravity wall designs I've ever seen, because it just isn't done very much. So you might get a chance to design one of these, but I kind of doubt it. But that's definitely one kind of gravity wall. Crib walls are not at all uncommon. They seem to be more common outside of the U.S. than in the U.S., but you can still see them places. And again, we talked about this. There are both wooden and concrete ones, but most of the ones are reinforced concrete ones. And these are sort of like Lincoln logs. Do they still have Lincoln logs? They're basically like Lincoln logs. You just kind of stack them up. And then you fill them with a really high quality fill material. And you do need to worry about the internal structural design for those, and there's some design guides for that. There's a lot of precast modular wall systems, and I've uploaded for you in this section the guidelines for this particular system called double wall, and for another one called the T-wall. I think that's right. We'll see in a second. But this is the double wall system. There's a bunch of these systems out there, and they tend to operate a lot like crib walls, but the internal design for them is very proprietary. So it's kind of hard to understand how they design them. But these things stack up. They give room for this high quality fill in between them, and then that system is acting like a mass against the external failures. So this is a little snapshot out of their design guidelines. These things come in different sizes, and they show you how to stack them up. And the external design, I need to back up for a second and cover that, is pretty straightforward. But the internal design, you've got to be careful, see that they don't fail. And how you do that, they give you some design for it. It's hard to understand where the design guidelines came from. T-wall is a very common system. In fact, I think it's even treated specifically in the FHWA manual because it is one. It's called a T-wall because in these cases the facing units look a lot like T's, and you stack those together, and they are generally built on a batter like this. And in this case, they don't have a thing on the back to hold the soil in like the crib walls or that double wall system, but this stem, if you want to think of it, sticks back into the soil. Well, you can build them either battered or straight. Here's a picture of the key wall system, and this is the shear key that they place. I don't know if you can tell, but they have these little shear keys to prevent sliding. We're going to talk about external versus internal design, but one of the things you have to check is they're sliding, and they have these little shear keys there, and they've got a fairly important detail about how to put them in. They're masonry keys, and you put them in, but they're wrapped in this foam so you don't get cracking. It's a fairly, I don't want to say it's complex. It's an interesting little design. It's obviously proprietary. There's the shear key. And a gabion wall, this is the one we're going to design. This is a real common wall system. In this case, you basically have mesh wire baskets that are holding very select fill. Often it's stone. In this case, you can see these it's made out of some rectilinear stone pieces, and they're actually stacked in there by hand. So it's not, it can be just dumped in there, but more often they're fairly carefully placed. And these things are usually put together to build a wall like this is kind of back on a batter. All right, so external versus internal stability. If we go back to, I think I put the slide away. If we go back to, or think back to the cantilever wall design we just did, so that we have the same 4 basic, or 5 if you want to count global external failure modes. We've got sliding, overturning, bearing capacity, and settlement. That's true for all these walls, as we said at the end of the previous lecture. Then and we have to check those for all the walls, and that's going to control the external geometry of the wall. Once we're done with that, we've got to check the internal stability. Now, I didn't say it this way when I was talking about the cantilever wall. I talked about the structural design of the wall. Well, if you want to really think about it, that's the internal stability design, or the internal design of the wall. That's what's ensuring that that wall that you build stays together one piece and acts as one piece, so that those external failure modes that you checked are valid. If the wall falls apart, it doesn't matter what external failure modes you checked. So we very explicit. I didn't use the same language when I was talking about cantilever walls, but it's really the same thing. We have internal designs and external designs for these walls, and the external designs are essentially the same. So in our external design, we're going to have our loads. It's the same for all the systems. We're going to determine the earth pressures, and we're going to check sliding, we're going to check overturning, we're going to check bearing capacity, and we're going to check settlement. Now, the free body diagrams we use for each of these systems are going to be slightly different, but it's the same thing. So that process is going to be the same as what we did for cantilevered walls. And the internal design is a different thing. The internal design, we're essentially checking for sliding at the interfaces between the elements of the wall, and for bearing at the interfaces of the elements of the wall. And I'll show you what I mean. And then for these, there's always some structural capacity for these systems based on how they were designed. So there's some kind of a structural capacity check for each of the systems. So we'll start with the simplest system, which is a gravity wall, which is a dry stack gravity wall like the very first picture we saw. And you're saying, well, what's the internal failure modes for this? Well, it's really pretty simple. We're going to start first. Sorry, I skipped the earth pressure. Generally, we're going to use a Coulomb earth pressure with this one because it works better. And we're going to just pick the back face of these things isn't very smooth, but we'll pick the smoothest plane that goes against the backfill, call that the edge of our free body diagram, calculate the weight of this thing, we apply our earth pressure, and then when we do, and we'll do the external checks just the way we did, but the internal check, we're basically going to take a free body diagram at some point in the wall, we're going to apply the earth pressure diagram to that part of it, and we're going to calculate the normal and sliding friction along that face of it. And in this case, we're going to have to check that the reactions in the middle third, because this particular method can't carry any tension, right? This is just a bunch of dry stack stones, can't have any tension, so we got to have compression all along the thing, or else it is going to fail at the back. We're going to check for sliding. In that case, we're going to find out whatever the friction angle is for a rock, and that could be a really high friction angle, particularly if it's all interlocked. We could have a friction angle greater than 45 degrees, easy. So it could be a really high friction angle, but we want to check that it can't. This is our structural failure of the wall. If you want to think about it, is that wall shearing apart. So that's the internal design for a dry stack masonry wall. So you just got to do these checks down the way. You probably don't have to check every foot, but you run these checks down the way, and you might have to. This is why, by the way, when you do this, you end it with a really fat wide base, because that's how you keep the whole wall in compression. You got to have a fat wide base to do that, since there's no tensional capacity. So that's why these walls get really, really wide at the base. All right. Well, what do you do with these proprietary systems? Well, if I take a free body diagram through that, I have to apply my earth pressure. I got the weight of whatever's above this wall. I've got some shear and some normal force there. Again, these ones don't have any, there's no ties at the back holding them together, so you want to be sure that this reaction force is in the middle third, or else you have tension back there. And if you got tension back there, they're not going to be holding together. And then we're going to check for sliding. Now in this case, there's this little key in there that's specifically designed to mitigate sliding problems. And the actual design of that and the sizing of that, you don't have any control over. You don't know what they did. They're going to give you some design guidelines, and you're going to hope that they're right. So my caution with these things is that if you've got a critical design with these things, if you're doing a 15-foot high wall, it's probably not an issue. But if you've got a critical design with these, you better spend some time talking to the designers and satisfy yourself that they're doing it right. I spent some time with 2 of these companies trying to get them to give me some information about the internal design so I could sit here and talk to you about it, and I spent a couple hours trying to get it, and after that I just gave up because there wasn't any hope. But if you've got a big project going on and using these things, you want to be sure that you don't have a structural design because they made a mistake. So in this case, the the shear design is you've got definitely this normal force times whatever your interface friction angle here is between your units, and you could look up the interface friction for masonry on masonry. And if you want to think about that shear key, it's kind of like cohesion. In other words, it's a shear resistance with no normal force. So it's not really cohesion, but if you want to think about it, for a geotech, it sort of looks like cohesion. It's basically some kind of shear resistance that doesn't require a normal force. So the real question is, there's your interface friction. The real question is, what is that key capacity? Well, these guys will tell you what it is, and if you're happy with that, and you're satisfied that they've done their homework, then fine. But in this case, it's not generally something that you can check from general principles. I think these things are checked mostly through full-scale structural testing. But again, they haven't. It's definitely proprietary, and at least I didn't spend a huge amount of time. But they weren't. The guys that I got hold of weren't particularly interested in explaining to me how they design those things. I don't know if it's because it's really proprietary and they didn't want to tell me, or some stupid-ass professor they didn't know, they didn't want to talk to, or they didn't know what the hell they were talking about, so I couldn't really tell. But I don't know. I like stuff I can check, and I don't know how to check that one. You structural engineers can probably think of ways to check it. Okay, well, let's talk about gabion wall. And by the way, so I'm looking at this T-wall system because it has a fairly simple interface model. You basically have sliding plus whatever this key capacity is. Some of the other ones are much more complicated, but there's got to be some way to check that internal stability. And oftentimes for these things, it's proprietary. All right, so let's look at our gabion wall. So this is the one that you're going to do your design exercise for. I've given you the design guidance from Maccaferri. It's Maccaferri 1995. It has most of the, I'm going to go through most of it here, but it's got all the stuff you need there. They have a nice little program. If you do want to do this stuff, there's lots of gabion wall design programs out there, but they have a nice free one which you can download. I was going to show it to you, but my version doesn't run on Windows 8, and I haven't checked to see if there's a new version. It's got kind of a old interface. It's not a fancy new program, but it's a really nice, easy way to design gabion walls. And in fact, it even has a real simple global stability check in it. So, and if you want to download it and use it for this design problem, that's fine. Make sure you do some hand calculations to back up the design. And you just need to go to the Maccaferri site and you can download it. I think that you download it and then you email them and they'll send you a password for it. So I would commend that to you. So this is our earth pressure diagram. Again, we usually use Coulomb with a, am I getting that right? I think so. With a friction angle here, so delta probably should be about 2/3 of phi because you're definitely going to have a soil-to-soil interface there. And then our internal design, we go to each level in the, it should be obvious that the places this can fail internally are along these horizontal interfaces. So we just go to each one of those, and we have to check the interface capacity for each level. And the nomenclature they use, they talk about B, and when they say B, it's the width parallel to the interface. It's not the horizontal B. It's the B parallel to the interface. We've got the active earth pressure and a weight acting there, and then we basically going to operate in this direction because it's convenient to operate in the direction along the angle of the interface. There will be some eccentricity to the loading, and you will assume that again has a linear distribution of stress along the base of the gabion. So that's our free body design. If you do that, you can, if you make this assumption about it being linear, then you can calculate that the maximum normal stress here at the toe of the interface section is going to be Rn over B minus 2E. And so you have to do the following internal checks. The first one, you're going to check that the reaction stays in the middle third for the reasons we've already talked about. And then the next thing you're going to check is that these gabions don't crush, because you're going to have those two gabions on top of each other, and if the stress is too high, you can actually crush the gabion, and then it's going to start to deform. And then we need to check sliding across the face of the gabion. So those are the three checks that we need to do. One of the important things you got to do is you got to know the mass of the stuff in the gabion, and they have an interesting way to do it. Instead of doing a gross unit weight of the material, because these gabions often have very, very dense material in it. Remember that picture we had where these, where's my photograph? Where these stones are stacked in there like that, you know, that's pretty dense. That's getting really close to the actual density of the rock. So their approach to actually calculating the density of the fill is not to calculate unit weights of the fill, but actually to calculate this is essentially the density of the rock material itself. It's a specific gravity times of the minerals times unit water. So I mean you notice those are like reinforced concrete densities, right? Higher than them. So that's the density of the actual rock material, and then you assume a porosity for that, and then calculate your density based on the porosity that you think you're going to get based on how you're going to install the material in the gabions. So if you got rectilinear pieces like that last one, and you're going to go and hand stack them in there, you might have a porosity that's down like 10% or 15%. If you're going to loose dump it, by the way, 40, there's a porosity of 40 is a very loose material for cohesionless material. Those of you that took 531, you could go back to check. Remember we did the maximum minimum densities based on spherical packing and stuff. You can check those. That's really loose. So rather than calculate a unit weight for the material grossly, you calculate the unit weight of the rock, and then come in with your I mean, this is your equation right here. So the gross unit weight is the unit weight. This is essentially of the mineral solids times 1 minus the porosity, and this is just a little design chart to do that. So that's kind of interesting. Their design for the interface is all empirical, and it's all based on testing some pretty much full-scale testing. So they actually built gabions, put them in a big-ass compression machine, and tested them in compression to see what capacities they could hold. They actually did direct shear tests where they put gabions together and put the interface in a vertical orientation, and then sheared them. They did full-scale wall tests. They basically built 2 gabion walls back to back, and then put water bladders between them and filled them full of water. So here's a picture of that test. So there's quite a bit of empirical design stuff here. By the way, Maccaferri's not the only designer of gabions. So there's lots of gabion designs out there, but they're one of the oldest and I would say technically most thorough ones. So our internal stability, we're going to use this diagram that we just developed to check our internal stability. The first thing we're going to do is check for the crushing of the gabions. So from their empirical testing, they get this allowable stress, that's from doing this, this test right here. Obviously, the compressive capacity of that's going to be dependent on the density of the rock as well, the gabion in it, right? I mean, if you want to think about it, this is kind of like a spiral wound column. What the gabion material is doing is really providing a hoop stress to the stone material in the inside, and it's then basically, you know, it's very much like you design a spiral column for your structural guys. It's basically providing a hoop stress to keep compression, radial compression on the material inside, so it can take a higher vertical stress. So this is a completely empirical design thing, but it seems to work. Where was I? Right here. So 1.14 times the gross density of the stone material minus 43. This is all in pounds per cubic foot. I'm pretty sure. Make sure you check the design guidelines. And then you just want to check that this maximum stress that you find there is less than that allowable stress. That's an allowable stress. Don't ask me how to do gabion walls for LRFD design. I don't know. Oh yeah, there I go. Pounds per cubic foot. How about that? That was nice of me. Everything's in pounds per cubic foot. Then we're going to check for sliding. Now in sliding, we've got two components of sliding. One component of sliding is our regular frictional sliding. I'll talk about that in a second. And the third one is these gabions they're not just stacked on top of each other. You actually tie them together. So you got these little ties that you tie the baskets together. Well, that's a shear resistance when you tie the baskets together. So there's an interlock between the baskets that also provides the resistance. So there's two pieces of resistance there. This interface friction angle, again, a completely empirical number, but again, it's based on the gross unit weight of the material that you're putting inside, minus 10 degrees. And this CG, which is the cage shear resistance, this comes from the ties that you put in the cage. So it depends on the gauge of the cage and how much of that mesh is in there. So it's 0.68 times PU minus 72. Well, PU is the weight of mesh per the volume of, whoops. It's how much of the gabion material is in the basket. So you have both denser meshes and thicker wire. So there's the way you can get more material in there is either by having a thicker material that makes up the basket for the gabion, or you can have the holes in the chicken wire can be closer together, or you can have thicker wires. Does that make sense? And so what it's essentially doing, if you want to think about it in structural terms, it's sort of like an area of steel in structural design. You know, the more area of steel you got, the more resistance you're going to have. So it's kind of like that. Rather than going there and actually calculating some mechanistic way about how it's behaving, they're just looking at the gross area of the gabion steel as a function of the volume of the gabion and using that as a way to determine what this I don't want to call it cohesive. What this sliding resistance is based on the steel itself. So that's again completely empirical. This PU number you look up in the designs. Again, it's based on the size of your gabions and the mass of the stuff you put in. And generally, just as a rough number, it's about between 2 to 6 pounds per square foot. I'm sorry, I think that's cubic foot. I think that's a cube. Again, check the guidelines. And then you want to check that your shear force divided by B, right? So that's your shear force. This shear force is actually going to be in pounds per foot because it's going to be into the board, right? Into the projector there. So that over B is a stress, and you want to make sure that that's less than its allowable stress right there. So again, very much like the T-walls, we have a sliding friction term, and then we have this shear key term that's not a function of the normal stress. And the shear walls, it's that little, in the T-wall system, it's that little block that you put in the back of it. In the gabions, it's actually the gabion material itself. And that's it for the gabion design. So this is your design problem for you to work on for the next week. See if you can have them done by Tuesday. I'll see if we can actually get some grading done this week. Questions. So I'm not covering bend walls. I'm not covering crib walls. The overall process is the same. You're going to have an external design based on the geometry of the thing, and there's going to be an internal design. In internal design, you're going to check for crushing and sliding and all that kind of stuff. The details of how you do that for each one of those designs is going to be different, but the basic process is the same, and I thought doing one of them was enough. Because if you end up having to design T-walls, you're going to go learn a T-wall system. Does that make sense? Let me show you a couple things let me stop the recording. Any questions?
How do you ensure the weight of the gabion? If you have two workers working on either side?
You know, that's a really good field QC thing. I've never installed it. So the question is, how do you ensure that you actually have the mass you designed for in there? So, I mean, my professional response would be, you want to do some, you know, you want to do some modeling in the field and figure out how you're going to do it, you know, and test a few out. And then you need, but that's a really good field QC thing. If you're expecting to hand place all those things in there, and you got a porosity of, you're down to a porosity of 35, and you found the guys are just bringing an end loader and dumping it in the gabions. By the way, you don't want to just dump in the gabions anyway, because you're gonna bend the wire on the sides. So you can't just dump into them. You've got to be a little bit careful about how you place it, because otherwise you're going to deform the gabions, and then they don't stack straight, and they don't go upright, and then you got a big problem. So you can't just dump into a gabion anyway. There has to be some handwork there. So that's a great question. Never built one. But definitely something you want to be concerned about.